So when the golfer hits the ball, it bounces into the hole. Each time the golf ball moves upwards, it's going to gain gravitational potential energy. Each time the golf ball hits the ground, it changes shape. As it changes shape, this is going to store elastic potential energy. And when the golf ball is moving, it's going to have kinetic movement energy. Each time the ball hits the ground, energy is transferred away from the ball. How can we tell this? Well, if you look at the diagram, we can see that the amplitude of each bounce gets smaller and smaller over time, and that tells us that energy is being transferred away from the system. So if we write the height of the bounce decreases. The next question is about electromagnetic spectrum, and you've got to put the missing parts of the spectrum. Okay, now it's ordered from long wavelength through to short wavelength. A, right in the middle, is going to be visible light, and B is going to be X-rays. Which EM radiation is used for heating and night vision? Well, infrared waves are the ones that are associated with heat waves. Which are used for cooking and satellite transmissions? Well, microwaves, as in a microwave oven, and in mobile phone signals. And the list of electromagnetic radiations from radio waves to gamma rays, as I said earlier, is in order of wavelength, but it's also in order of frequency. Now we've got to pick the right one here. As I showed earlier, it's decreasing wavelength. Radio waves have a long wavelength, gamma waves have a short wavelength. For this question, you've got to explain how electromagnetic radiation can be harmful to the body. Now you've got to choose two types of radiation. There are a number of choices you could make for this, but really we're looking at the high frequency waves that are the most dangerous. So we're looking at things like gamma rays, X-rays and UV. Well, let's start with UV waves. Okay. What are their harmful effects? Well, exposure to UV rays can give you an increased risk of skin cancer. How can you reduce this risk? Well, if you're going out sunbathing and things like that, then one thing you've got to make sure is that you apply skin protection sun lotion. For the next radiation, I'm going to choose to do gamma, but what I say here could equally apply to X-rays too. Again, we're looking at increased risk of cancer if you're exposed to too high a dose. And how do we prevent that? Well, essentially reduce exposure time. And it's unlikely in your day-to-day life you're going to be exposed to many gamma rays or X-rays. If you go to hospitals and you have a scan, a CAT scan or a normal X-ray, then you're going to be exposed to X-rays. But hopefully, in a lifetime you won't have so many of those that it's a significant risk. Similarly with gamma rays, your main exposure is going to come from medical images, things like that, and reducing exposure time is the best way to reduce the risk. Right, so the first thing we've been asked is to estimate the length of the pencil and give its unit. Well, looking at the scale here, if we're looking at this side, we're closest to 0.5 centimetre on that scale, and over on this side we're closest to 17. So I'm going to say 16.5, and we're measuring that in units of centimetres. Suggest two ways that the student could improve the accuracy of this measurement. Well, at present the pencil is on the centimetre scale side and not on the 0.5 centimetre scale. So what we could do is we could move the pencil to the other side of the ruler. So move the pencil onto the other side of the ruler to use the more precise 0.5 centimetre scale. The other thing you'll notice is that the pencil is not set at 0, okay, so we've got a kind of 0 error as we measure. So I'm going to say position the pencil so that it starts as close to the 0 centimeter mark as possible. Right, here we're looking at an electric motor. Now we're asked, when the switch is closed, the coil spins. Why? Now when the switch is closed, we're going to get current flowing through the conductor. Okay, now I think that's the positive side there. So the current is going to flow this way through the wire. It's hard to see from the diagram, but we'll assume it's flowing this way around the coil and out to there. Now, as soon as we've got current flowing through a conductor that's in a magnetic field, okay, then we may well get motion. Now, the magnetic field is going to be across here. Again, it's difficult to see which side is which north and which is south, but what we know is that at some points within the coil we've got current that is cutting across the field at 90 degrees. Okay. Now as soon as we've got current and a magnetic field at 90 degrees, we can apply Fleming's left-hand rule to give the direction in which that conductor will experience a force. Okay. Now in terms of explaining why the coil spins, when current passes through a conductor, it creates a magnetic field around it. Now this magnetic field around the conductor will interact with a permanent magnetic field, which is drawn in red in the diagram here, and the interaction of the two magnetic fields is going to exert a force on the conductor, causing it to spin. And state two changes we could make to make the motor spin faster. Well, the first is to increase the strength of the permanent magnetic field using a stronger set of magnets. We could also increase the current through the coil, which we could do by stepping up the voltage or reducing the resistance, or we could use a larger number of turns on the coil. Now, the student then changes the circuit and replaces the battery with a switch and a lamp. When they spin the coil by hand, the lamp lights. You've got to explain why the lamp lights. Well, hopefully you can see here that instead of running this as an electric motor, we're now running it as a generator, and that by spinning the coil we're turning kinetic energy into electrical. Now the idea here is that as we spin the coil, the conductor, which in this case is the wire, is going to be cutting across the lines of magnetic field. And then as the conductor cuts across these lines of magnetic field, it induces a voltage across the ends of the coil, which causes current to flow inside the coil. Question 5, we're looking at a laptop computer which a student opens with an upward force of 4.2 newtons applied 0.25 meters from the pivot. Now state the equation that links moment, force and distance. Well, moment is force times distance, but we need to be a little bit more specific, that moment is force times perpendicular distance from the pivot. Now we're going to use this equation then to calculate the moment of the force that opens the computer. So moment is force times distance. Now we're using 4.2 newtons of force at a distance of 0.25 meters from the pivot point, and that gives an answer of 1.05, and they've already given you the units for that, which is Newton meters. The student finds that 4.2 newtons is the minimum upward force needed to open the computer. Then the student applies a downward force to close the computer. Explain why the minimum force needed to close the computer is likely to be less than 4.2 newtons. Well, when you're closing the door, the force that you apply is not going to be the only force which is trying to turn this laptop lid in an anti-clockwise direction. Oh, sorry about that. Now the downward force that we apply to close the lid, okay, produces an anti-clockwise moment, but that's not the anti-clockwise moment, the only anti-clockwise moment in this situation, because we've always got at the same time the weight of the laptop lid. So now we've got two anti-clockwise moments. We've got the force that we're applying to the edge of the laptop, and we've also got the weight of the laptop. So we don't need to apply as much force, because at the same time we've got the extra moment due to the weight acting in that direction. So the downward force F is not the only force causing an anti-clock, and the weight of the laptop lid also provides an anti-clockwise moment. Right, question 6. Light from an object forms an image in a plane mirror. Tick the 2 correct statements. Well, the first one is true. The image in a plane mirror is virtual. That basically means that no real light rays come to our eye from that virtual image. Okay, when you see an object normally, the light rays that come into your eye come from that object, but when you see a virtual image in a mirror, the light rays don't come from the position that you think that image is in. And the next one that's true is the angle of incidence equals the angle of reflection, which is always true. Use words from the box to complete the labels on the diagram below. Well, this is the normal line, and the bottom surface is the mirror. The student then investigates the formation of an image in a plane mirror using the apparatus in the photograph. She uses the holes that the pins make to construct this diagram. Add to the diagram to show how the student could find the position of the image. Well, the image is going to be the image of the object here. Okay, so what we're going to do first of all is we're going to draw a straight line. You're going to use a ruler that crosses the mirror at 90 degrees. At the same time, we're going to extend this line here. Again, you're going to use a ruler until we hit a point over here, and this is going to be the position of the image. We're then asked, how could the student confirm the position of the image is correct? Well, what we can do then is we can measure using a ruler this distance here, okay, and then on our diagram we can check that it's the same as this distance here. If we call this D1 and this D2, then D1 should be equal to D2. Right, question 7 is about a kettle, and we've got a Sankey diagram which shows how energy is transferred within the kettle, and we're asked what is the efficiency of the kettle. Well, we have to look at the input energy and the useful output energy, and what I can see here is that of the 100% of energy that goes in, I'm getting 90% back out as useful energy, so 0.9 is going to be the efficiency. Now if I want to calculate that using an equation, efficiency is useful energy out divided by the total energy in, so it will be 1800 divided by 2000, and that gives 0.9. Now the heating element in the kettle obviously gets hot when it's switched on. Why does that happen? Well, we're going to say that there's going to be a high current, or at least a current, in the element, and as that current flows through the heating element is going to have a resistance, okay, and the resistance of the heating element causes electrical energy to get transferred into heat or thermal energy. For part C, we're told that the kettle has a power output of 2000 watts and it's connected to a 230 volt main supply, and we've got to give the equation that links power, current and voltage, and that is power is voltage times current. Okay, or if you remember a triangle, if for those of you who like those, we could give any of the 3 equations that fit that. So V is P over I, or I is P over V. Show the current that the current in the heating element is approximately 9 amps. Well, we want current, so we're going to use this one here. Okay, so I is P over V, which is 2000 divided by 230, and that gives a current of 8.7 amps